Hello students. So we will do the chapter 8 today. So we're going to start a new chapter. But before that, there was some confusion during the live session that one student asked like what is the steps for finding out the whether the system is stable or not based on the Nyquist criterion. So for that, remember that we are looking at the open loop transfer function, and the system could be something like this. So the system is like this. This is a feed forward transfer function, and then you have feedback system HS and the summing point, so minus and plus, and this is how it is, right? So this is RS CS. Okay, so the open loop transfer function is in this case is GS times HS, and the closed loop will be, this is open loop, and this is closed loop, right? So closed loop transfer function will be equal to simply GS divided by 1 plus GS times HS. What we are interested is in the closed loop transfer, the closed loop system. We want to know whether the closed loop is stable or not. Based on what? Based on the open loop analysis. So we will analyze this one. So we are going to analyze GS times HS only. And what we do? We are going to plot it. Plot what? So plot G I omega H I omega, plot this and angle G I omega and H I omega. So this we plot in what we call it Nyquist, right? So the plot could be, let us say, could be something like this. Say, let us say the plot is like this. Yeah. Okay. So, and this plot is based on the original, the contour in S plane. So this is the contour, which is like, and this is r equal to infinity. So what that is, right? So this is the real S, this is imaginary S. Yeah. So here we are finally going to find out check the stability for this system, the closed loop system. Yeah. Okay. But remember that if we let us say this is given by PS over QS, right? So this we can write what? Equal to GS divided by plus 1 plus PS over QS, and which will be equal to simply GS, right? And then we will have QS plus PS, right? So plus PS, right? And divided by QS. It will be something like this, right? Okay. So basically, what it means, basically, how finally this can be written as multiplied by QS, right? Like that. Okay, QS times PS here. Okay. So how do you know the closed loop system is stable? Stable if QS plus PS has no root on the right S plane. That's what the stability means. A closed loop system will be stable if there is no root on the right half of the S plane. That's what that is. That really means this equivalent to no root of QS plus PS on right half S plane is equivalent of saying that no zeros of 1 plus PS over QS on right half S plane. Right? Zeros, because automatically this becomes 1 plus QS plus PS divided by QS. So no zeros on the right side of the S plane. Yeah. So this is equivalent to this one. So as long as we make sure 1 plus, now I go back to the original, the general purpose original general purpose statements. If 1 plus GS times HS has no, that really means has no zeros on right S plane, right? No zeros. Remember that the 1 plus QPS divided by QS and PS over QS have the same zeros, meaning that 0 of one is the 0 of the other. Hence we know the 0 for GS and multiply by HS, right? So if you know 0 of a GS times HS, we know n, how many times it is encircling minus 1. We know that. How many zeros are there? We know, because both of them have same zeros. So number of zero of this is also equal to number of zeros of this. So number of poles of this, number of poles of this is equal to poles of this. Both have the same pole, right? PS over QS and 1 plus PS over QS, meaning that the GS times HS and 1 plus GS times HS, same poles, hence P same. Now both have same P and number of encirclement about minus 1 is known, n. Then we can find out Z is equal to n plus P, right? We can find out n we get from here, from the Nyquist diagram, and P we get from the open loop system, from GSHS, right? So both have same number of, exactly the same poles, hence we get the number of poles from there. And based on that we can find out number of zeros of 1 plus GS times HS system. We can find out this number of zeros of that. Okay, number of zeros of this is equal to number of roots of the closed loop system, right? Remember, we are going back here, right? So this G is equal to number of roots of closed loop system, right? And this will tell you number of roots of closed loop system on right S plane, yeah. So this G will tell you what is the number of roots of the characteristic equation of the closed loop system on the right side, and hence you can find out whether it's stable or not. That's what it is. Yeah, so that's why just think in that way, and you will find that all connected. What we are studying in root locus, we are just looked at the characteristic equation. Here we are not looking at the characteristic equation. Indirectly we are looking at characteristic equation, but we are talking in terms of zeros, poles and all those things. But finally, our aim is to make sure that the roots of characteristic equation are not on the right side of the S-plane. That's what the aim is. I hope this clarifies. Okay, if not, please let me know. For more clarity, we can also compare these methods. Okay, so before we go to the next chapter, let me also compare all the stability criterions. Yeah, so this will also summarize what I have learned so far, and also we will understand that all these are actually same. What they are saying is actually same. So let's just start with, let us say we have a 1 over s minus 2 is our system. This is what the GS is. Okay, so this is like this one, and then we have HS. So HS equal to unity, just take 1. Yeah, so and here we have minus, here plus. Okay, so this is RS and this is CS. Okay, so start with Routh's stability criterion. Yeah, so Routh's okay, so here we have to see the funnel control, the closed loop. Yeah, so Routh stability criterion always looks at the closed loop. Yeah, so it has to be, unless the system itself is open system. So closed loop transfer function Ts is given by, in this case, what do you get? You get 1 s minus 2. Okay, let's write it like this one, k over like this. Yeah, just k, because that if it is, we will find out for what value of k it is stable or not stable or unstable. So we have k over s minus 2, then 1 plus 1 multiplied by k s minus 2. Yeah, and that will give us equal to k over s minus 2 plus k, right? That's what it gives us, right? So like this one. So or equal to k divided by s plus k minus 2, right? And we can here we know that all the coefficient has to be positive, right? So 1 is there, k minus 2 has to be positive, and it will make a stable, right? So or you can write like this one, s1 is 0, and we have s1 is 1 and s0 is k minus 2. All has to be positive, and that tells us k minus 2 has to be greater than 0, and hence k greater than 2. So from Routh's stability criterion, we can actually, we are getting k greater than 2, it will make it stable. Okay, so this is done. Now we can go to now root locus. Let's say in root locus, so what do we get? Yeah, so in root locus we have like this. So for this one we have for root locus it is understood that k is already there, and then we have multiplied by s minus 2, right? So we have like that already. So for s minus 2 we have to plot. Yeah, so it's understood that we are plotting for different k. For s minus 2, we have, this is the pole, which pole is here, right? And this is minus 2, and there is only 1, right? So what we get is we have the root local which goes like this one. Yeah, and we know that the k here, the value is k equal to, this will belong to k equal to 0, right? This will be what, the to be k equal to 0, and here at infinity it will be k equal to infinity, right? K equal to infinity. Right here, what value we have, we can put it there and find out. Yeah, so at this point we have the when s is equal to some value, right? So you can find out, and that has to be on the root locus, right? So we can find out. So how we can find out? So for the closed loop system, we got to find out the closed loop system. The closed loop, we know that T naught S equal to K over S plus K minus 2, right? And here the root is, if root is 0, then S plus K minus 2 has to be equal to S, because S is 0, right? That really means K minus 2 equal to 0 and K equal to 2. So basically this point belongs to K equal to 2. So we can find out, right? So that means at K equal to 2, this is just getting a stable from onward. So, and from here onward, we have K greater than 2, basically, right? And then the root will be on the left half of the S plane, and that will make it stable. So this tells us, since the anywhere on the left side will be stable, and hence the K greater than 2 will make system stable. So from this we find out like this one. Now let's look at the Bode diagram. Right? So let's see whether we can find out anything about it. So here for Bode plot, just we look at the open loop transfer function. The T naught S is equal to K over S minus 2. Now we will, let's keep, we don't know K, yeah, so but we can plot it for, so we assume K equal to 1, yeah, and after that we can fine tune it. Okay, so we have the like GS times HS is equal to nothing but 1 over S minus 2. So for this one we will draw, and based on that we will try to find out what is the meaning of for stability what to do, right? So 1 over S minus 2 is there, right? So that means our G I omega times H I omega will be 1 over minus 2 plus I omega simply, right? And hence we have this G I omega H I omega magnitude will be simply equal to 1 over root under 4 plus omega square, and angle Z I omega H I omega will be equal to 1 over 0 minus angle of minus 2 plus I omega, and will be equal to minus and tan inverse omega minus 2. Okay, so not to be confused here, we can find out exactly where it is. From here looks like sine is positive, omega will vary from 0 to infinity, and cos is negative, right? So sine positive, cos negative. Okay, so sine positive is here, sine positive is here, right? Okay, and cos is negative, and cos is negative is here, right? So we are talking about this one, yeah. So this one is here we are talking about, yeah. Okay, so look at, we can find out some values. So of course we have to write as log 20 log, and G I omega times H I omega, right? will be equal to nothing but minus 20 log of this, right? So will be minus 10 log of 4 plus omega square simply, right? So that's what we have to plot. Now take omega is very, very small. Omega tends to 0, right? And in that case, what do we get? We get simply this k, or this is what the gain is, right? So this is k. So what we get is minus 10 log, or 4 plus omega square, you get minus 10 log of 4 plus log of 4. That's what we get. And value of this we get at omega equal to 0, close to 0. And this we get angle we get equal to minus, and this is 0, sine is 0, cos is minus 2. Yeah, so we can think like that. So it's a ratio basically. So from that we can say that this is 180 degree. Actually this tells you 180 degree. So minus that makes it minus 180 degree. Yeah, so this is what we get to begin with. Okay, now we omega equal to in this case we can make omega equal to 2. Yeah, so omega equal to 2. Okay, then what happens? Our k, right? So this becomes minus 10 log 4 plus 4, 4 plus 4, right? And we get minus 10 log 8. Yeah, and angle is equal to minus 10 minus and tan inverse 2 cos, sine is 2, cos is minus 2, minus 1, and since this is in the second quadrant, so value is like this one, so angle will be 135, so will be minus 135 degree simply. Yeah, okay, done. Sorry, not minus, okay, minus, and this is 135, so minus 135. So and now omega tends to infinity, and then what we get? If omega tends to infinity, then our value of this will be what? You can see here. So this infinity, and then this becomes equal to the infinity, and hence this value becomes 0, right? So what we get is minus 10 log, and here we get 4 plus infinity, so we get a very big number, right? So this will be like minus infinity and so on. Yeah. In fact, we can write when omega is very, very large, we can write this minus 10 log 4 plus omega square becomes equal to minus 10 log omega square only, and becomes minus 20 log omega. So basically what you see, the linear, it is linearly decreasing basically, right? So instead of writing this one, we can write this way, and from there we can, if omega is large, we can also have angle, right? Omega tends to infinity, and the angle can also be here minus tan inverse, and this we have very large, right? So infinity minus 2. Yeah, so what we get, again we are talking about this, will be here somewhere. Yeah, so we are talking about a value which is not from this side but this side, where the sine is getting infinity, but the cos is negative, right? Cos is negative. So we are talking about some angle which is little more than 90 degree, almost 90 degree, right? So this will tells you 90 degree, so equal to minus, and this is 90 degree, so it gets a minus 90 degree. So what you see is minus 180 degree, minus 135 degree, minus 135 degree, this is minus 90 degree, yeah, and then accordingly. So we can plot that this side, yeah, and we will see. So let's plot the Bode diagram. Okay, so Bode's diagram. Okay, so we will start with omega equal to 0. So let's do like this. So at omega equal to 0, yeah, we have minus 10 4, right? So this is minus 10 log 4. So here we have minus 10 log 4, right? Okay, at omega is 0, close to 0, let us say, yeah. And then after that, this one we have omega, yeah. Okay, now next is omega equal to 2, and that time this becomes minus 10 log 8. So let's see, this is minus 10 log 8, yeah, here somewhere. Okay, and so this becomes at omega equal to 2. So let's say this one is omega equal to 2. So omega equal to 2, and then for infinity, so this goes like this, thing like this one, yeah. Okay, and for omega, big omega, we have like that. Okay, now similarly, let's look at this one. Not to forget that we are plotting log omega, right? So this is log plot, yeah. So this is log omega, and then this this equation is minus 20 log omega. So that means when from log omega equal to 1, right? Log omega equal to 1, this is like this. So here we have log omega equal to 1. Right? So this is log omega equal to 1. So at this point, from here, okay, somewhere it will be 0. So let us say this is 0 is somewhere here. Here it is 0. So extend like this one here. So at this, from this on, this becomes something like this. Yeah. So this becomes linear. Yeah. From here, it will be like this one. Okay. Before that, so here, so this one is the asymptote I have drawn. Yeah, so the actual value are somewhere else, right? So it will like this one. So it will start from here, and then here it will be somewhere here, let us say, and after that it is this is going to be, so this is going to be something like this, yeah. So it is going something like this one. It will go down like this, yeah. Okay, now accordingly we can have the angle basically, right, like this one. Okay, so here we are plotting angle of what? Angle of g I omega, h I omega basically, yeah. And we know that as omega equal to, here this is a log, yes, log omega. So at omega equal to 1, that is log omega equal to 0, and at this point, okay, we have to see, okay, at omega equal to 2, at omega equal to 2, what do we see? This is 135 degree. omega is large, and then it starts from 180 degrees, so minus 180 degree. When omega is 0, almost 0, then it is minus 180 degree, then we have minus 135 degree, and then we have minus 90 degree. So let us say this is minus 90 degree. Okay, so minus 90 degree when this becomes larger and larger. So it starts at 180, and then at omega equal to 2, it goes like this. So it will be something like this. So this is what the plot is. Yeah, so this is our phase diagram, goes from minus 80 degree to minus 90 degree, and here this goes something like this, okay. Now let's look at the margin. Okay, so minus 180 degree when phase we have, then we have this point. So we said this is distance from here to here downward was phase, what we call it as the gain margin, right? So gain margin, in this case, gain margin will be equal to 10 log 4. Yeah, okay. Well, and what is the phase margin? Okay, phase margin when this is 0, but you see it cannot be 0. So that means somehow the phase margin here is not defined. Okay, something is wrong there. Okay, so clearly we cannot approach the gain margin, K margin method here because of actually it's not defined. It's you cannot find out. Okay, so then probably not a good idea to look at it from a stability point of view, but still we can find out a few things. We can find out what is the condition when phase margin and gain margin both are 0, meaning that we are going to match minus 180 degree here and 0, K equal to 0 here. Okay, so meaning that how much we can shift of what? So one way to shift will be exactly at when we have omega equal to 0, close to 0, then we have the value is minus 10 log 4. So we want, instead of passing from here, what we want is we pass this curve from here. So we lift by this much. Everywhere we are shifting it by this value. How much? This value. Which value? We are adding 10 log 4. Yeah, we are adding 10 log 4, and then we will see that where we have minus 80 degree at omega equal to 0, we have the gain we have 0. We are now starting from, we are shifting from 10 log 4 to 0. So for that we have to add to the present, whatever we have the present one, we have to add this much. Yeah, and then in that case you will see adding to gain plot gets us 0 phase margin, the 0 gain margin and phase margin, gain margin plus phase margin. And we know that this is the boundary of the stability, right? From here we can measure. Yeah, so how is it possible? We have drawn here for 1 over s minus 2, right? So if we shifting up really means that multiplying by this k, so that when you take log of 20 log of this, you will 20 log k, and then this, what you get? You get 20 log k, and then you get minus log s minus 2. That's what you are getting, right? Okay. And this value, the one you are finding it here, is this one is plotted for this part, right? This part minus like this one, and you are adding these to make a 0, right? So that really means what we get from that is adding this much, meaning that we have 20 log k is equal to nothing but 10 log 4, right? Equal to 10 log 4 or equal to 20 log 2. Yeah, and that tells you k equal to 2. That what tells you is at k equal to 2, the phase margin and gain margin both become equal to 0. Yeah, so this at least tells you the boundary where it is marginally stable, and after that if you increase it, right, this is the original one corresponds to k equal to 1, the shifted one is k equal to 2. Yeah, when you have k equal to 2, exactly it passes through, it starts from 0 where the phase is minus 80 degree. You increase k more, let us say it is here like this, yeah, here, then what do you get? Then you can get like for example here, and this like this one, from here to here. If k is more than that, let us say k equal to 5, k more than 2, right? Then you get this one is what you get, a phase margin, right? You get a phase margin here, yeah, but what you get is the gain margin, what you get is negative, right? So your phase margin you get positive and gain margin you get is negative, right? So obviously because of this s minus 2, because it is not since the root is not positive, because of that you get complicacy. What we studied, the phase margin and gain margin, was for when you have the roots on the negative side, yeah, then it will follow, both of them will go down. Here what we get, one coming down, the one goes up, and because of this we see one is positive, then other is negative. Yeah, so because of that is happening. That really means that the Bode diagram method we cannot apply to this one, and we have to be careful about it. And hence actually we did not study anything about stability using Bode diagram. Bode diagrams just tell you, especially looking at k, what you can do with k, that's what it can tell you. Here, for example, you can get the marginally stable at k equal to 2, that at least we get the boundary. So k equal to 2 is the critical value where we can get the boundary basically, right? So marginally stable. Okay, now in this respect, yeah, so again the Nyquist stability criterion we can use. Okay, and we can see, actually we can see what is the meaning of that. So these values, these are still relevant, these that we are going to use. Instead of Bode diagram, we will now use the Nyquist plot, and we will see whether we are able to find out k for which it will be stable or unstable. So let's plot the Nyquist diagram. So this will be, okay, so one line here and like this one. So what we get at omega equal to 0, we have, although we have taken a log, but basically we have taken log of the g I omega h I omega, right? 20 log of that. So we get simply in this case we will get, you can see here, when omega equal to 0, we have the value of GH is equal to 1 over root, right? That's what we have, right? So we have 1 over root 4 plus omega square, omega equal to 0 will be simply 1 over 2 only, okay? And what is the angle? Angle GH is equal to, we get angle equal to minus 80 degrees. Angle will be relevant. So what is the point here? Point will be half. So let us say this is the half here, right? Half. And then minus 180 degrees. So that's why we have this side. Yeah. So this one is done. Okay. Now let me write here omega equal to 2. Yeah. Omega 2, and then what is the value? GH is equal to. So put the 2 here. So we get 1 over root 4 plus 4 equal to 1 over 2 root 2, right? Okay. So 1 over 2 root 2, and what is the angle? Angle is minus. Okay, this one is minus 135 degree. So minus 135 degree is where? It is here, right? This is here, minus 135 degree, and where is the? So if let's say it's half here, it's half here, and this is in between somewhere, right? So here, this will be here. So this point is from here to your value, from here to here is 1 over 2 root 2. Yeah. Okay. And this is for omega equal to 0, and this one is for omega equal to 2. Okay. Now omega equal to infinity. Omega to infinity, we have value angle equal to minus 90 degree. So omega infinity, we have the value equal to 0 to begin with. Yeah. So put omega here, 1 over root 4 plus infinity, that becomes 0. So value will be here, and minus 90 degrees. So it should go like something like this one, right? So if you draw it, what we get? We get like this. This is what the Nyquist plot will look like. Okay, so it will be anti-clockwise from 0 to 2 to infinity, and that is when omega is positive, and omega negative, if you plot, it will make a complete circle. So it will go like this. So what we see is anti-clockwise. We see anti-clockwise, and it is not encircling minus 1. So what we see in this case is we have here. So this is a half, and this is minus 1 here. This is right. So this is minus 1 over 2. Yeah. Distance from here to here was half. Okay, so minus 1, what we see here from here is n equal to 0. N equal to 0. Okay, now looking at the open loop transfer function, we know that on the right side we have one of the poles. So we know that p equal to 1, and hence this tells us that z equal to n plus p, right? So that is equal to z, and hence number of 0 on the right side will be 0 plus 1 equal to 1. For what? For k equal to 1, right? This we have plotted when k equal to 1. We have just taken k equal to 1 and we have plotted that. Now if you increase the k, what happens? There will be a time, like if you increase the k, you are going to just zoom it. So there will be a time when it will pass through minus 1, right? And then there will be another value which will go beyond minus 1 as well. Yeah. Okay. Now you can find out when exactly it goes to -1, and after what value it will go beyond -1. Yeah, okay. So how will you pass out? Okay, okay. Before that we do it, we know z equal to 1. What is interpretation? That tells you that there is 1 when k equal to 1. At least there is 1 0, which is on the right side. That really means the characteristic equation will have one root on the right side. 0 of 1 plus, it tells you 1 for what? 1 plus k over s minus 2 will have a 0 on the right side. That tells you the characteristic equation. That tells you that s minus 2 plus k will have a root on right s plane. That is tell you when k equal to 1, and that's true. When k equal to 1, you have s minus 2, hence you have one root on the right side. So that tells you that. Okay, now what will be the value so that we have exactly passing through -1, and in that case it will be marginally stable. Yeah, means it is barely stable, just touching right there -1. So in that case, what do you do? We are going to increase what? Okay, now look at it. At when omega equal to 0, this point omega it is 0. So if we zoom, -1 will come here, right? -2 will go there basically. Yeah, so that's how it is going to change. So see here, GH. Now we can exactly want that, and want what? We want the value at omega equal to 0, we want this to be equal to 1, then only it will pass. Yeah, and the angle will not change anything because k is not going to change the phase anyway. Yeah, so what we can write? We can write here k over root 4 plus 0, omega equal to 0, right, is equal to 1. Yeah, from here we will get, right? So instead of half we want 1, so we want to put a k here, k over root 4 plus 0 equal to 1 is equal to k over 2 is equal to 1, and hence tells you k equal to 2, and hence tells you if this passes through here, this circle corresponds to k equal to 2. Yeah, so this one is for k equal to 1, this circle here passing through 1 is k equal to 2, this will be for k greater than 2. Okay, now if k greater than 2, can you find out whether this is stable or not? Okay, so let's see. K is equal the k greater than 2, and what we find for k greater than 2, we will have one encirclement, right, but anti-clockwise. Yeah, anti-clockwise encirclement. So n equal to -1. Why is anti-clockwise? Counterclockwise, right? So this is anti-clockwise. So for k greater than 2, n equal to -1, and hence we can find out is z equal to, right, z equal to n plus p, n equal to -1, and p is equal to, we know that there is a pole is minus 2, there is one pole, so you can write 1 equal to 0. It tells you there is no 0. If k greater than 2, it tells you there is no 0 of what? Of 1 plus k over s minus 2. It tells you there is no 0 of this, no 0 of this. That really means it tells you the characteristic equation of the closed loop transfer function, which is s minus 2 plus k equal to 0, will have no root on the right side of the s plane, and hence it will be stable. Yeah, so we looked at different stability criterions, yeah, different stability criteria, and we are actually doing the same thing. What we are doing? We are actually seeing the characteristic equation only, right? But from different approaches, and we are trying to find out the value of k for which the roots of the characteristic equation are on the left hand side of the S-plane to ensure the stability. So this is what all about. So we have done all these things, the stability criterion and all we have studied, because finally we should be able to design. Yeah, and design, when we say design, that really means we have to control some unstable system, right? Something which is, for example, the aeroplane, for example, right? Unless we control, it is quite, like unstable system. Yeah, so you have to control it. So that's why you have a lot of controls fitted there, and that's why it controls it. Yeah. Same as like when your motor and which has a, say, flywheel. Yeah, you give a torque and it will keep on running. If there is no friction, for example, it will keep on running. But what about we want to control it, meaning that I want to move it by a certain angle and then come back. For that you need to have extra system there, which is known as control system. So we have studied earlier that there is a plant here, right? So there is a plant, there will be some plant here, right? So we are starting the new chapter, right? This is chapter 8. So little bit we will study, and then in the next video we will go into details. So if there is a plant, we don't know what kind of, either we know that it has some transfer function. So transfer function either known or unknown. So known or unknown, right? So on one of these two. So far we have assumed that it's known. Yeah, it's known, and hence if it is known, then you should be able to exactly find out what is the, so here it is, unity feedback loop. So goes not like that, and there will be a controller here. Yeah, so here there is a controller, and controller, we have a controller, and it will come here. We have input, it goes like this. Yeah, so this is minus, so this is plus. Yeah, and goes like this, right? So RSCS. Okay. Okay, so same like the two types transfer function of the plant may be known or unknown. So if it's known, then whatever we have studied, we can have that. So the maybe it's the plant may be of the first order, let us say. So we can have 1 over tau s plus 1 kind of transfer function, let us say. Or second order, we will omega n square divided by s square plus 2z tau omega n plus omega n s plus omega n square, right? So first order, second order, or any order, or any kind, right? So if it is known, then you can analyze it. You can try for different things. Either you will have compensator, right? So compensator, or you can have PID controller, right? So this is proportional, integral, derivative control, right? So compensator will have transfer function something like tau 1 s plus 1 over tau 2 s plus 1, and it may have a the gain as will multiply, and you are going to fine tuning it, meaning that you can find out tau 1, tau 2 and k value such that you get the overall transfer function, open loop transfer function in that, your GS in that case will be, let us say, with compensator, you have tau 1s plus 1 over tau 2s plus 1 multiplied by k multiplied by 1 over tau s plus 1, let us say. So you have GS this one, and for that you can do all the analysis that we talked just now also in earlier the whole control systems lectures. So this you can analyze, you can find out what should be the value of whatever you require. You can, the parameters you can choose. Once you choose the parameters, you can build the controller using, for example, op-amp that you know, right? You use some capacitor, resistance, and you can find out type of compensator you want in electronic as a electronic device, and that you can use, right? So you can make it. So, but compensator is not the only type of solution. There is also depending on the type of the plant. Sometimes the PID, or most of the time PID controller is very useful. So for PID controller, the transfer function will be typically like this is Kp, this is P for proportional, plus 1 plus 1 divided by tau I s, I for integral, plus tau d, right? D for derivative s. So this is the PID controller will have all the three components all in series, or not a series, or all in parallel. So all of them are added. So basically, what do you have? You have Kp the time plus 1 over tau s plus 1 over plus tau ds, and this will be here, right? And then the in that case gs, if you have a PID, then this is with compensator, right? If you have a PID, then your gs may be given by Kp multiplied by 1 divided by tau is plus tau ds, and multiplied by this. Let us say you have that tau s plus 1, right? And then you do the analysis, whatever analysis you have learned, you can do all those things. Yeah. Based on that, you can find out what is the value of Kp, what is the value of tau I, tau d, and so on. But chapter D, we are going to also talk about what if transfer function is not known. Okay, so then we have some rules to follow. Okay, so in the next lecture video, we'll talk about that. When the plant does not, we don't know any transfer function for the plant, then what to do? What to do is basically we try to that we will study, but first we will do we give some kind of input, see what kind of output it has. Yeah, and then based on the output, we will find out some system parameters, and that we can use to find out these values. Which values? These values. Value of Kp, Ti, and tau I and tau d, we can find out based on the response of plant or some parameters that we are going to find out. And that's what we will study the next time. Yeah.